Kyle Taylor, a master's student in environmental engineering at the University of Florida. I'm going to be talking about my poster today, which is entitled Urine Treatment and Waterless Urinals, Cation Exchange and Precipitation Potential. So the overall goal of this project was to see if the problematic precipitation in waterless urinals could be solved by using cation exchange resin. Waterless urinals are not only used to save water, but also to provide an option of urine treatment at the source. However, there is a process known as urea hydrolysis, which is shown here, in which an enzyme known as urease breaks down the urea found in fresh urine and turns it into hydrolyzed or aged urine, increasing the ammonia and ammonium concentrations, bicarbonate, and raising the pH. This process induces the precipitation of two minerals in particular, struvite, which is a magnesium phosphate mineral, and hydroxyapatite, or HAP, which is a calcium phosphate mineral. The formation of these minerals in the unit's pipes leads to maintenance issues and odors, which often detracts from user acceptance and overall feasibility of the units. So ion exchange treatment, specifically cation exchange treatment, is depicted here in this picture. CER, or cation exchange resin, is shown here. Cation exchange resin is a small bead which has charged ions such as sodium, which when they enter into a solution, in this case it would be urine, the sodium ions will come off of the resin bead and different cations will be adhered to it and removed from solution. Here we see the removal of magnesium and calcium. That was the goal, to remove magnesium because that was the limiting element in struvite formation, and calcium because it was the limiting element in HAP formation. So the first thing we were trying to determine was whether or not magnesium and calcium could be removed from fresh urine through cation exchange resin treatment. First thing I needed to do to test this was to make a synthetic fresh urine solution that contained about 4.1 millimoles per liter of magnesium and 4.7 millimoles per liter of calcium. And it had urea, and the pH was about 6. So this all represented the average found in human urine. I took a sample of the synthetic fresh urine and dosed it at different doses with the cation exchange resin, and allowed for the resin in the urine solution to mix, after which time it was filtered and the remaining solution was analyzed for magnesium and calcium by titration and ion chromatography.
Good.
So this is the first results graph from the first part of the experiment. You can see on the x-axis the CER dose in milliliters per liter, and on the y the calcium concentration over initial concentration. You can see that calcium has very good removal along the range of cation exchange doses. The initial calcium concentration was about 4.7 millimoles per liter. You can see at the highest dose of 40 milliliters per liter, only about 10% of that calcium is remaining in the urine solution. Magnesium, the initial concentration was about 4.1 millimoles per liter, and you do see good removal throughout the cation exchange resin dose. However, it is not as great of that as calcium. At the highest resin dose, about 50% of the initial magnesium remains in the solution. This is another results graph from the first half of the experiment. You can see the concentration in solution of magnesium and calcium given in millimoles per liter on the x-axis, and the concentration on the solid or resin surface given in millimoles per gram of dry resin on the y-axis. So as the concentration of the calcium in solution increases, the uptake onto the resin surface increases in turn. However, for magnesium, as the concentration in solution increases, the uptake onto the resin surface does not increase. In fact, it remains pretty much steady and actually begins to decrease. So this highlights the cation exchange resin's removal preference of calcium over magnesium. So we were able to show in the first half of the experiment that magnesium and calcium was able to be removed through cation exchange treatment from fresh urine. The next part was to see whether or not this would have an effect on the precipitates that were formed. I wanted to test this by starting off with an aged synthetic urine solution. The aged urine was copied from that of fresh urine, except that it did not have magnesium and calcium because I wanted to be able to control those levels, and the urea had been hydrolyzed, which meant that there was a high bicarbonate concentration and a higher pH. So the first thing after I made this aged synthetic urine was to take samples and dose it with magnesium and calcium stock solutions. The levels of magnesium and calcium stock solution that was dosed into each sample represented the remaining levels of magnesium and calcium after each of the cation exchange resin doses. So for example, with the highest cation exchange resin dose of 40 milliliters per liter, we saw about 10% remaining calcium in the solution and 50% of the magnesium remaining in solution. So the very last sample was only dosed with about 10% of the calcium and 50% of the magnesium. So after the calcium and magnesium were added to the aged urine, it was mixed for about 15 minutes and precipitates were allowed to form. We then filtered it and analyzed the remaining solution, again for magnesium and calcium, and collected, dried, and weighed the solids that were caught in the filter. Here we have the first results graph from the second half of the experiment. You can see the cation exchange resin dose in milliliters per liter on the x-axis and fraction of magnesium and calcium precipitated on the y. And even though we were able to see magnesium removal with cation exchange resin treatment, at every resin dose, 100% of the magnesium is formed into the solids. However, with calcium, we saw that the amount of calcium formed in the solids decreased as the resin dose increases. At the non-ion exchange treated sample, about 85% of the calcium formed in the solids, and at the highest dose of 40 milliliters per liter, only about 40% was formed in the solids. Again, this is 40% of the 10% of the calcium that was remaining after the cation exchange resin treatment. So here's the second results graph from the experiment. You can see again cation exchange resin dose on the x-axis and mass of solids precipitated in grams on the y. For the sample representing no ion exchange treatment, about 0.18 grams of solids were formed, and you can see it steadily decreases until the highest resin dose of 40 milliliters per liter when there are almost no solids remaining. This is very promising. It shows that cation exchange treatment does have a dramatic effect on the amount of solids that are formed in each urine. Overall, this set of experiments was able to show that cation exchange resin can remove magnesium and calcium from fresh urine, and that this treatment is able to reduce the fraction of calcium precipitated and the overall mass of solids formed. This shows potential for the use of cation exchange resin in waterless urinals to prevent the problematic precipitation of magnesium and calcium phosphate minerals. I'm Kyle Taylor, and that's WaterWeUpTo.